Okay, good afternoon, everybody, and welcome to this Global Food and Environment Institute at the University of Leeds webinar, which is today given by Dr Daya Pandey. My name's Tim Cockerill. I'm a professor in the School of Mechanical Engineering at the University of Leeds, and I'm going to be the chair for the seminar today. I'll just briefly introduce Daya before he makes a start. So Daya's an assistant professor within the Institute of Thermofluids in the School of Mechanical Engineering at the University of Leeds. He joined us about a couple of years ago from the University of Hertfordshire, having previously had a number of academic positions within the UK and overseas. His current area of focus is on low carbon energy systems, particularly circular bioeconomy based systems incorporating elements of energy and nutrient recovery. And that to some extent is the focus of his seminar today. So just in case you're not familiar with these seminars, the presentation will last for about 20 or so minutes. We'll then allow 15 or so minutes of questions. If you do want to raise questions, please put them in the Q&A section and I'll relay those questions to Daya when the main seminar has finished. So assuming you're ready, Daya, please feel free to get started.
Yeah, thanks, Tim. Thanks for the kind introduction. So hi, everyone. I'm Daya Pandey. So this talk is focused on circular farming, how we can harness the animal waste for energy as well as nutrient recovery. So before we begin, just to give you an overview, this is the World Bank report. It's called Water Waste 2.0, and it's highlighted the waste management issues and how it is going to be evolving over the period of time. So at the moment, we are currently generating about 2 billion tons of municipal solid waste, which is supposed to be increased by 3.4 billion tons by 2050. So there's a certain need for the sustainable waste management processes. And if we break it down, regional or also category-wise, what are the different type of waste that we are generating? So metal, glass, and if you look at the right hand side, the food and green waste, that is the majority of the municipal solid waste or waste is being generated. So that is the one part of looking into municipal solid waste. And if I'm going ahead and looking into animal waste, that's where the talk is main focused about. Just to give you a bit of context, if we are looking as a whole globe, as per 2023, this is FAO data, Food of Agriculture Organization. So this data shows that in 2023, if you are looking the total vertebrate animal population on the planet, it's 1% is only in the wild. We as human beings are about 32%, and 67% are farm animal. And if you're wondering what the farm animals are doing, they are basically feeding us, looking for the meat production and protein, basically the protein intake that we are using. However, it's accounts. So if you're raising those 67% farm animals, you require significant amount of agricultural land to raise those livestock that then feed back to us as protein. So the data shows about 75% of total agricultural land is just being used to raise those livestock, and that's roughly about 35% of total land surface area. So a significant amount of the land being used to house and raise the farm animals. So because it's a huge sector, and if I put in the context, is one of the major contributor of greenhouse gas emissions. It contributes about 1/3 of the agriculture sector. So coming from the GHG emission, this sector employs, of course, there's a positive thing because it's a big sector. So it's employ about 1.3 billion people, contribute about 40% of total agriculture GDP, and it provides 1/3 of humanity protein intake. In the UK, agriculture sector contributes about 48 million tons of greenhouse gas CO2 equivalent emissions, where 71% is mainly nitrous oxide and methane that's coming from manure. And if you look, the last figure is, if you are looking carbon dioxide, the net zero when we're looking into carbon emissions, reducing the carbon emissions, is merely 1.9% carbon dioxide emissions coming from the agriculture sector. And this is the latest agri-climate report that was published by DESNES and government of UK. So how this sector governed? So if you're looking at typical farm, it houses about 20 to 80,000 bird per shed. And in terms of our intake meat production here in the UK, is about 80 to 100 million broilers are slaughtered for protein for the meat production in the UK. And because of that high demand of broiler, particularly the poultry meat, it generated about 300,000 tons per year. And if you convert into equivalent energy, that could be a source of 3.45 petajoule of energy. This is the reason of this sector is heating is main energy consumer. So if you want to raise the chickens, you have to provide the comfort and energy efficiency. And in that part is mostly energy consumption come from the heating purposes because it's still a cold country. Another important figure to compare with the other European countries, our average heat demand per bird is slightly higher compared to the EU recommended guideline, that is 0.33 kilowatt. Nevertheless, several poultry farm where is the more concentrated, like Walkenham poultry farm in Shropshire, they are already processing the waste generated from the farm to produce the heat that goes back to heat the shed and reduce the reliance of heating on fossil derived fuels. There's further plans is coming up. DEFRA has also planning to set up another 5 megawatt thermal facility that is in collaboration with NFU, National Farmer Union, and Cargill is going to use that. And this is supposed to be set up in Herefordshire, again, poultry sector. Why this is needed? Because if you use those huge amount of animal waste, and if you put on the surface land, there's not enough land to uptake. And if you put on the land, it could lead to ammonia, nitrous oxide, and odor emissions. And it could leach to the groundwater. The contaminants can leach to the groundwater, cause groundwater contamination. And the nutrient that's mostly nitrogen, phosphorus, sulfur, they could again run off with the water, and they could also pollute the surface water, causing eutrophication. And there could be also a source of vermin and pathogen. However, it's not all bad what it is about, but if we recover this, we manage this waste in a sustainable way, so we can use this for energy source, but most importantly, we can also recover energy that can again sustain our farming without reliance on fossil-derived fertilizers. So this talk is particularly, so there's several paths to treat sustainably the animal waste. This talk is particularly focused on thermochemical conversion processes. So just for the audience, if you are looking into thermochemical conversion processes, that can be categorized in combustion, gasification, and pyrolysis. And if you say what are the what is the difference between those processes, is basically how much amount of air we are feeding into the reactor or into the process. So if we are putting no external air into the process, that is basically called pyrolysis. And gasification, when you are putting, you are not burning it, but you are trying to convert from one form to another form, is called gasification, when the equivalence ratio is 0.1 to 0.4. And combustion, I think everybody knows, when we burn something, it produces heat. Look into the automotive engines and others. So the combustion is more prominent technology. Even if you are looking power plant, they always run on combustion. And our main goal in combustion to ensure that fuel is properly combusted so that we can get the maximum amount of heat. So we always put equivalence ratio more than 1 to ensure that proper fuel consumption. And if you look all three processes, it leads to a different product. In combustion, it's mostly heat, and then you can utilize the heat for heating purposes or producing power. In pyrolysis and gasification, you will get bio-oil, char, and gases, syngas, depending on the quality or the temperature you are operating. So again, this will lead to three main products: the gas, or liquid, and the solid product, that is biochar, including ashes. So they can utilize those processes and look into what is happening. So in terms of pyrolysis, it can be, so if you do pyrolysis, this is in the absence of air or oxygen to decompose your waste or biomass, whatever you are taking into a solid bioproduct. And if you do the pyrolysis process, is always lead three product: solid biochar, including ashes, liquid as a bio-oil, and then of course there is some pyrolytic gases that is happening, that volatiles released into gases. And this product yield depend on the type of biomass what you are using or the waste you are using, and then their solid residence time and the temperature when you are operating. So I just give you here a bit of information. Depending, so when you are trying to design your pyrolysis unit, you have to decide what is going to be your end product. So if you are more interested in producing biofuel, the fast pyrolysis process could be the most interesting process if you are looking in liquid production. But if you are main focus looking into biochar production, maybe slow pyrolysis would be the most appropriate process to look into it. So even if you're looking, so why I chose poultry litter? Because we are talking about thermochemical conversion processes. So you don't want your waste or the feedstock to be so much wet. So you want to ensure that it is not having high moisture content. So that's why I chose poultry litter compared to if you are looking cow manure. So because it has a lot more high moisture content, about 70 to 80%. Here, if you look the proximate analysis, so volatile matter is good that we can convert this much into energy, but also look into the ash content where it's about 14%. This could be a source of our nutrient, that's where the inorganics are, and if we can use it for sustainable farming. And if I'm looking into the ultimate analysis, and this is just I want to emphasize that this is based on dry and ash-free basis. I want to emphasize because I was looking into what is the actual heating value of the poultry litter compared to wood pellet. So if you look this table, carbon, hydrogen, nitrogen, the energy carbon and hydrogen content is slightly higher than compared to traditional wood pellet. However, nitrogen, sulfur, and chlorine that could lead to contaminants, they are significantly higher compared to wood. But if you look, the calorific value is very comparable, and it shows that this kind of feedstock could be a valuable source for the thermochemical conversion processes and can support the thermochemical process. Because my aim is also to look into nutrient recovery, so I did the ICP analysis of the ash to see what are the inorganics present in the poultry litter or the ash when you generated. And you can see here the phosphorus is again a very important element for a plant, for agriculture sector, and it is very geopolitically sensitive. So rather than relying on African country, Morocco, and some other places where the phosphorus is in abundance, we can recover, and if we sustainably process this poultry litter, we can recover the phosphorus that can support the local agriculture sector. And of course, it will improve the farmers' income and reduce the reliance on fossil-derived fuel, helping to achieve the net zero target in agriculture sector as well. So when I start looking, initially the idea was I was more focused of recovering the energy. So I introduced this poultry litter into fast pyrolysis process. The result you can see is not as good as I was supposed to be. So in fast pyrolysis, normally we expect more organic liquid to be produced, but here you can say is biochar concentration is a lot higher compared to organic wood or gases. The reason behind this is the amount of ash content in the feedstock, and that leads to high biochar content yielding from the pyrolysis process. Another important fact that I found out is when I looked the bio oil that is produced from poultry litter, it has very high calorific value, but also it has very high number of tan number, so total acid number. And when total acid number is quite high, you cannot use this kind of bio oil to put in your engine or boiler, because it could be acid, it is acidic, the acid number is very high, so it could be corrosive and it could damage your equipment. But this type of, if tan number is very high, this could be used as a lubricant. So if you are producing pyrolysis based poultry litter bio oil from this kind of waste which is having high tan number, those bioliquid is not good for biofuel production, but rather we can use for the lubricant production. Looking into that process, the recovery of the nutrient and ash. So on an average, most of the nutrient, the major and minor nutrient, we recover almost 70 to 80%, except nitrogen. Of course, during the devolatilization process, nitrogen get devolatilized to form ammonia, and it gone into the gas phase. So you lose nitrogen, but of course we have plenty of nitrogen. So our main focus was to look into phosphorus and potassium. That's NPK, the major nutrient. So phosphorus and potassium was the major factor to look into the recovery. And we were able to recover about 80 to 90% of phosphorus and potassium. And then once we produce the biochar, we look into the pot trial test. We did a pot trial test in cassava plant. So when it was just controlled soil without biochar. So on the left-hand side, you can see the plant growth when it was not infused with biochar, and on right-hand side, when the soil was infused with biochar. And you can see the growth rate of the plant is significantly better compared to when you are looking into controlled soil. So it shows that it is a promising result in terms of plant growth. But we also looked into plant availability of the biochar that we produce from intermediate process. We look into fresh and also a pelletized form of chicken, poultry litter. And in both cases, we found out the phosphorus, when you go through the thermochemical process like pyrolysis, it forms very stable compound, and it doesn't solve in the water. That means it indicates that the amount of phosphorus that is present in the biochar, you put in the soil thinking that this is plant available. The answer is no, it is not available to the plant. It is stored in the soil, but it's not available to the plant because it's not water soluble. And that triggered another problem to see how we can solve this problem. So of course, if you are seeing this reduces the eutrophication problem, because it's not easily run off with the water to go in the surface water to cause the eutrophication. But again, it's not available to the plant. So you are basically nutrient loading soil, but it's not helping the plant growth. One thing I want to mention here, we found out that one specific temperature, again, it has to be revalidated and do further research is required. We found out the biochar that produced at 500 degrees centigrade, it meets the European Fertilizer and Product Regulation. And if you are thinking what is European Fertilizer Product Regulation, so it's regulate what kind of component material can be used or classified as fertilization product. So this particular biochar, if you produce and if meet the guideline, you can sell to the fertilizer company and it can be used as a component material for fertilization. I also looked into the byproduct during the process. Some of the fly ashes we recovered, and there's also UK guideline produced by DEFRA. So it says if you're meeting those criteria, you can use this as a nutrient, but if you are not meeting, it could be treated as a hazardous waste. So you cannot put in the soil, you cannot put in the land. It has to be treated as a hazardous waste. So again, we found out that all this inorganic alkaline metals, they are exceeding the limit set by the DEFRA. So again, the poultry litter fly ashes cannot be used as a fertilizer to put in the soil, because you are going to contaminate the soil rather than improving the soil. Similar fact we found, so we looked into again leaching effect. So as I mentioned, it was not water soluble. So we also look into ammonium acetate and also with the hydrochloric acid. So we're looking into where they are soluble, where they are washing off. In case of phosphorus, 26% by the water, 12% by ammonium acetate, and majority of the phosphorus was washed by the hydrochloric acid. So certainly we need to do something about it. It cannot be used as a fertilizer or put in the soil. But phosphorus, in terms compared to phosphorus, potassium was better leached by the water. So it is a lot more available to the plant, and it can be used as a nutrient in the soil. So to summarize, we have demonstrated that it has enough energy resource that can sustain the farm in terms of their energy requirement. And we have also demonstrated that we can recover the major and micronutrient to support the agriculture sector. The pot trial test shows the plant growth in early stages is quite good when your soil is amended with the biochar. But again, we have to look how this alkaline earth metal that is exceeding the criteria, how they are going to affect our food chain, and how they are looking into the process, where they go, are they staying in the soil or transferring into the food chain. Recovery of NPK was very good, and we found out particularly one certain temperature where we can produce biochar that can be used as a component material. And finally, as I have demonstrated, that given the low plant availability of phosphorus in biochar, it is probably more efficient to use as a component material to produce a fertilizer through the chemical processes rather than putting biochar directly in the soil. So that's the end of my talk. I'm thankful for several funding bodies that have supported so far my research work in this area. And thank you very much for listening. And I would be very happy to answer any question if you have. Thank you.
Okay, thank you very much for that, Daya. So I'd encourage people, please, to put questions in the Q&A. Oh, that's an interesting effect there. But I've got one or two maybe to get started just while people are thinking and typing. So I think you partly touched on this on my first question, but could you give us an idea of the scale of the opportunity here? I mean, in terms of the scope, let's say, contributing to UK carbon or international carbon removal objectives. Oh, I think you're muted still, Daya, actually. Yeah.
Yeah, thanks, Tim. So in terms of, as I mentioned, looking into greenhouse gas potential of this sector particularly, so of course the carbon footprint of the sector is quite low. So an amount of carbon emissions coming from the livestock sector is about, or agriculture sector is 1.2, about 2%. But another potent gases that nitrous oxide and methane, that are the two major GHG emitters. So if we are looking into a net zero perspective, this sector will play a very significant role in achieving, and it's also hard to abate sector. So looking into manure treatment processes where we can utilize the biogas or manure to produce energy to abate the methane emission, but also looking into if we produce organic derived fertilizer, this will also reduce the reliance on fossil derived fuel, and it will reduces the nitrous oxide emissions as well.
Okay, thanks. So we've got one audience question now, which is about whether you've considered other contaminants, so plastics, pharmaceuticals, and so on. Presumably, I guess the questions are focused on the stability of the biochar with respect to those, rather than their availability. I know this is a big concern. The Environment Agency and other organisations are concerned about this with anything that's put on the soil. So have you considered those aspects at all?
Yeah, thanks, Kelly. Thanks for asking this question. So far, I haven't looked very specifically about plastic or pharmaceuticals. So it was more looking into the morphology and analyzing the ICP analysis of biochar, what is the inorganics present in there. So I haven't looked specifically to your particular question that you're asking, how much amount of contaminant in the biochar. But again, if you are looking into, so it's totally depend on the feedstock, where the feedstock come from. So if there's a plastic or pharmaceutical content in the feedstock, this will definitely transform into the biochar as well. So just to give you in poultry litter, a lot of calcium, suppose, is come from the feed. So it's not literally from feces, it's coming from the feed that is given to the chicken. So, and also they eat, and they also spread a lot of amount. So the calcium and other elements come from the feed that is given to the chicken. So just one example. So again, it reflects on the feedstock, where the feedstock originates from, and that will definitely have different type of contaminants.
Okay, thanks, Daya. So we're getting a theme of questions here. So there's another question here from Jane about whether water solubility is a good guide to plant availability for phosphorus and presumably other things, and whether you've tried, you've looked at, done some trials or whether others have done to see if the plants can use the phosphorus after, or the P rather, after addition to the soil.
Yeah, thanks, Jane. So we looked into so the water solubility is a parameter where how much phosphorus is being soluble into the water, and that if it is soluble in the water, this is assumed. Again, the plant uptake efficiency, again, you have to convert how much it is taken by the plant. So we plan to do a pot trial test, but again, there was not enough funding, so we couldn't perform further tests. The idea was to, once the crop is harvested, to see how much nutrient gone in and how much is remaining in the soil, to quantify how much nutrient is taken up by the plant. So first question to your question for the good parameter. So in my experience, I think the whatever soluble to the water, that's I have taken as a plant available, because you don't want to leach it with the ammonium acetate or hydrochloric acid to because if you put this, your plant will not survive in those acidic environments. So that's why I said, like, it's about looking into plant availability, what is the water soluble. For the second part, further test I need to carry out to see how much phosphorus remains in the soil after the plant harvesting.
Okay, so we're getting a few questions here. I mean, it's I'll just follow up with one of mine actually before we move on to Judith, which is more of an observation. And certainly there's in the work we've been doing on biochar, certainly we've found there's an essential tension between the desire for stable biochar and the availability of nutrients. In a way that, this is very simplistic, but in a way they're almost kind of opposite requirements. So I don't know if you've got a comment on that.
So not really in this particular field. So because I was looking more into plant growth and pot trial tests. So maybe if you are looking the the biochar stability in terms of different applications. Suppose if you are looking in energy related area, so when you are trying to produce anode, cathode, and all those material, or looking into water purification, maybe there is more important to have more stability of the biochar and activated carbon aspects. But in my area, I was looking more on the plant availability on the nutrient side.
Right. Okay. So you've not really, the stability has not really been a factor directly.
No.
Yeah. Okay.
No.
Interesting. Yeah. Okay. Yeah. Okay. So, gee, this fourth question is for like at the other end of the supply chain. So it's about the availability of litter. I think you gave us some data on that, but there's a interesting question about the, if you like, the competing demands for litter and what the kind of scope is for your approach compared to the competing demands.
Yeah, so poultry litter, I think there's also a European guideline. It was, thanks Judith. So this is classified to be used as a fuel on the farm. There's a European guideline. I can share the detail later. Probably Sarah can put it somewhere. So if you are using poultry litter at farm level for fuel products, as a fuel for energy production, it is allowed. So coming back to the second, I have given the figure. So it has a significant amount, about 300,000 tons being generated per year, and it has potential of 3.45 petajoule of energy. So it's significant enough to sustain the farmers' heat demand. Even sometimes it's much more that they have to flare the heat when they combust, suppose if you are using the combustion unit. The demand for poultry litter as a manure, yes, it has quite significant demand, particularly in mushroom industry because of having high nutrient value. So mushroom industry need, they like the poultry litter manure because it has better yield of the mushroom. Feedstock for AD is limited. The reason is it has high nitrogen content, and also is the moisture content is slightly less. So maybe unless you are going dry AD process, this particular feedstock, because of high solid content and high nitrogen content, is limited for the AD interest.
Okay, so there's good. You think there's good potential? Okay, for
dry AD.
Yeah. And what about, I mean, you didn't actually mention this, so it might be a bit of an unfair question, but that's kind of my job, really. So what do the economics of this look like? I mean, is it compared to the alternatives? I mean, that's probably difficult to answer, but give us your best guess.
When I took this area, so initially there was a lot of interest on this particular sector. I think alone, the payback period would be very long, but initially when it was launched by the government, so RHI, if you remember, renewable heat incentive, at that moment, the poultry litter based heating system increased significantly, but since then it's dropped. So again, the economics is not very strong yet in terms of commercialization.
Right. Okay.
So it does need incentives, some support from the government.
Right. Okay. That's interesting. We've had a interesting response. I don't know if you've seen it there in the Q&A from Jane about the desirability or otherwise of stability. So I don't know if you'd want to just comment on that, perhaps.
You want to explore nutrient from one farm to another? Yeah. Yes. I think. When I was presenting one slide, so the amount of nutrients litter or feedstock generated around the farm is a lot more. So you cannot use all those nutrients around the cropland that is nearby the farm. So of course, it needs to be transported to other places in arable farm. And you need to try and release it again. So I'm not sure what is this mean. Of course, you then need to try and release it again.
I think it's essentially your point, the point that you made there, Darren, that there's not sufficient local capacity. So you'd need to move, if you're going to make a market for this, you'd need to move, potentially move the produced biochar from one location to one further away. And obviously you want the content to remain in place while it's moved, I think. Yeah.
Oh, okay. Yeah, definitely. Yeah. I think it's when you produce the biochar, the nutrient or other elements, they are more stable form, so they are not just going to release during the transportation and other, so they will retain the quality of the biochar, so it's not going to affect with the transportation, but yeah, it has to be moved.
Okay, great. And I think we're more or less coming to the end of the questions there, Daya, but I'd just ask one more thing just while we're wrapping up, and that's what you see as your kind of future direction in this area over the next year or two. I mean, what other work would you like to do? Let's put funding on one side. What other work would you like to do? Yeah.
So definitely, I want to again test my hypothesis that where I claim that this is a component material that is fulfilling the European fertilizer and product regulation criteria. So if it is meeting, that's the win situation for me. So again, further repeats and do give a proper protocol that if you are operating at certain condition with this feedstock, you will get the quality biochar that is fulfilling the European product regulation protocol. So again, I think that will lead to the commercialization of the organic fertilizer industry. So that's the one direction I'm looking. But secondly, I'm also looking how to decarbonize the farm. So looking into energy recovery that I mentioned in the call. So use this, whether it's bio oil or probably the gasification unit that you can produce the syngas. You can further produce other chemicals. It can support at least the heating problem at the farm rather than relying on the fossil derived fuels.
Okay, great. So I think we're coming to a natural conclusion there. We've certainly given you 15 minutes of questions, which is what we promised. So thank you, Daya, very much for your great presentation. And thank you very much to everyone who's joined both within and outside the university, particularly for the questions and the discussion, which has been really good. So that's much appreciated. So thank you very much. And please look to Sarah Dennis's posts about future events that are in the Q&A if you're interested in hearing more. So thank you very much and good afternoon.
Yeah, thank you everyone for joining. It's been a pleasure talking to you all. So thank you very much. If you have any question, feel free to contact Sarah. She can pass on your question and I'll try my best to answer if I could. So thank you very much. Thanks for your time.